we talked about scatter plots. We talked about how to describe them. So we talked about form, direction, strength. We talked about whether they were linear, nonlinear, no association really, no pattern emerging. We talked about correlation. So correlation, what were the kind of main things to remember about correlation? Stays the same for what?
It's like add, subtract from the behavior.
Yeah, add, subtract, multiply, change units, correlation stays the same. It doesn't have units, okay? It's not resistant. Outliers greatly can affect it. What else? Correlation does not mean that the relationship we see is cause and effect. So if we see a strong correlation between two variables, it does not mean one's causing the other. Okay? We're missing a really big one. The association has to be linear. Okay? For correlation to be useful, our association has to be linear. Right? So we talked about those types of things last week. How to create a scatter plot, how to describe it, how to work with correlation to determine strength and direction, things like that. What we're going to do today is we're going to take that a step further. So seeing scatter plots and being able to notice a trend. With these two variables, we see a linear association. Or between these two variables, we see a nonlinear association. It's all nice to see those things, but what we want to do today is talk about least squares regression, which means we're going to take an actual line and fit it to our linear relationships. So we're going to be looking at linear relationships and how to actually apply a line to it so that we can use it to predict values. Okay, so the model, or the scatter plot itself is nice because we can see the trend, but we need something more if we want to start actually using that trend to predict certain values. What will happen if we have this value which wasn't accounted for? Things of that nature. So, when we create a linear model, basically what we're doing is calculating the equation of a straight line through our data. So we're going to take that scatter plot that we see with the dots scattered all over, and we're going to fit a line to it. Now, when we talk model, a model is just a way to represent the information. It's a way to represent the data. So when we look at this, it's going to approximate, and it's going to summarize the general pattern. So our line, is it very plausible that it's going to pass through every point in our data? No. If it's a scatter plot, that means the points are scattered around. A straight line can't pass through all those different points. Okay? So this is going to be an approximation. It's going to say this is kind of where we should be. This is our best fit for what we're looking at. So what we're going to be calculating is called the least squares regression line. So some terms you'll hear with that, you'll hear least squares regression line, or they might abbreviate it LSR. You'll see linear regression. You'll see the regression model. Okay, anything dealing with linear regression is talking about this regression line. So it's the line that best fits our data. And the big thing about creating this regression line, the reason we want this model is so that we can use it to predict outcomes. So we know there's a trend, we know there's a pattern between the two variables, but we want to use that pattern and try to predict what will happen if we have certain values that we're looking at. Now when you look at your regression model, slope is going to be a very key thing. And one of the things you're going to notice from today's assignment, every question pretty much is going to ask you to interpret slope. What does the slope mean in this context? Okay, so it's going to indicate the association and the rate of the association. So how fast it climbs or how fast it decreases, depending on whether it's positive or negative. And so our goal here, find the best fit for our particular association. So, if we want to use a regression model, we need to check three things first. And those three things are exactly the same way to check to use correlation. So like KJ said a little bit ago, correlation can only be used with a linear association. Well, same thing with regression lines. If we're trying to fit a line to a curve, it's not going to work out very well for us. Okay? So the three things you need to check before you start working through a regression model problem. Do you actually have quantitative variables? Because if you don't, you can't even create a scatter plot, which means you can't have a regression model. You need to make sure that the scatter plot is fairly linear to begin with. Like I just mentioned, if you have a scatter plot and the association is nonlinear, so it has some type of curve to it, it wouldn't make any sense to try to fit a straight line to a curve for prediction purposes. So it needs to be linear to begin with. And then, just like with correlation, we need to be mindful of any outliers. Your regression model, your slope, will not be resistant to outliers. If you have outliers in the data, it will greatly affect what happens with that slope on your regression model. So you check those three things to make sure that it's even worth your time going through the process of fitting a model to the curve. Okay? So here's kind of an example of when we might want to use a regression model. So right here we have a scatter plot. Now what they did was they went to Burger King and they analyzed a certain number of menu items. And they looked at two different variables. How much protein did that particular item contain, and how much fat did that item contain? Okay? So when they did that, this is what our association looks like. So if we were describing it, let's get some review with that. What type of form would this scatter plot have? Yeah, for the most part it's linear, okay? Which is good because that means if it's linear, I can use correlation or I can use my regression model. Okay? What about the direction? It's going to be positive, so it's going up. So as x increases, y increases. And what about strength? Yeah, moderately strong, pretty strong. Okay? So it's going to be kind of tightly clustered. So what we notice is, as we increase the amount of protein in an item, we also increase the amount of fat we can expect to see in that item. All right? Now, if all we have is the scatter plot, there's not much we can do with that. We can look for specific individual values and say, okay, well, this item had, for instance, 12.5 grams of fat or protein, and it had about 10 grams of fat. But we might be more concerned with a value that we don't have measured. So for instance, the question here, if you want to consume 25 grams of protein for lunch, so if you're on a specific diet that you have to have so much of a certain type of item, so in this case 25 grams of protein. If Burger King was your choice for lunch, how much fat would you expect to consume as well? So if you're trying to hit that 25 gram protein, how much would we expect to eat in terms of fat? So if we notice, we don't have any one single item that had 25 grams of protein, right? So we don't know exactly how much fat we would actually have. So what's going to happen is we're going to use our regression model. So they already kind of have the line drawn in here. We're going to talk about how to calculate the slope of that line, the y-intercept. So we're going to actually come up with the equations so that we can use it to predict. So when we write linear regression equations, we're going to write it in kind of a modified slope-intercept form. So think back to algebra. When I say slope-intercept, what was that? Y equals mx plus b. Y is equal to m, the slope, times the x variable plus b, the y-intercept. We're going to modify that a little bit for our purposes here. So in your book, this is the way they write their slope-intercept form. So when we write our linear regression models, this is the form we're going to have it in. Yes, it does. So the mark over the y, this little caret symbol here, okay, when you see that term, this is called y hat. Okay? So when you see that, that's called y hat. That little caret symbol above it, we just call that a hat symbol. Okay? Now, what's important about this? On a quiz or test, on the AP exam, on homework, if you write a regression model and you simply say y equals a plus bx, this is wrong. Okay? Y and x with nothing above them implies an exact value. Okay? But when we create a regression model, we're going to use a specific value of x. So this one is going to stay like it is, just x by itself. But we're using that x value to predict a value for y. So when you see this y hat here, this is a predicted value. It does not mean that if you had that exact x value in real life, you would get this exact y value in real life. So when we calculate these predictions with our regression model, they are just that. They're predictions. We think this is what it should be based on the trend. It doesn't mean that it's necessarily going to be that exact value. So when you write these out, it's very important that you do have that symbol with your y every time. Without it, you will be counted off. Okay? So x, that's the value of our explanatory variable. So here, it's going to be very important that you get your explanatory and response variables straight. You need to make sure that you have the correct variables and have them in the correct location. Because if you flip-flop x and y here, it wouldn't affect your correlation, but it will greatly affect what your line says. Okay? So x is the explanatory variable, y is for the response. And again, when you write it out, it's y hat when you're using a regression model. We are predicting that value for y. Okay? Another thing you may want to take note of, this is the way your book writes it. Okay? In your calculator, when we get to the point where we're going to use the calculator to create these regression models, they have two different options. When you calculate your regression model in the calculator, they have these two different options. So this one here is option number 4 in your calculator. When you go to the stat and calculate, this one would be option number 8. Okay? Now, if you notice, the first one, option 4, is in a slightly different format here. When I look at the way the book writes it, A here actually corresponds to what? The y-intercept. So A would be my y-intercept. And B would be the slope. Okay? Now, if I chose option 4 on my calculator, what's different? A is slope and B is y-intercept. Do you think that will change the value of slope and y-intercept for a given problem? No. The slope's still going to be the same. The y-intercept's still going to be the same. They're just going to be in a different order. They're going to be called something different. So when you guys do this in your calculator, be aware. The book writes it out this way, a plus bx. Your calculator, if you choose option 4, switches a and b. So they just have ax plus b. A is your slope, b is your y-intercept. Now, if you want to keep it consistent with the book, then you can always choose that second option, that option number 8. And if you notice, that one actually follows exactly what the book does, a plus bx. So when we get to that point, I'll leave it up to you which choice you make in your calculator. Just make sure you're always aware. The value on x is your slope. The value by itself, the constant, is your y-intercept. Okay? So now, let's talk about how to actually calculate these values. When you want to calculate the slope of your regression line, we're going to talk about how to do it by hand, using a formula, and by calculator. You need to know both. So you'll be expected to know how to calculate by hand and how to calculate with your calculator. So to calculate my slope, and we're using the formula from the book, so B denotes our slope in this case. We have this R times SY over SX. What do these values actually mean? What's the R? That's my correlation. Okay, so one of the things I'm going to need for my calculation is correlation. I'll need to do that in my calculator and figure out what my correlation for my two variables are. What is SY? Standard deviation of Y. So what's the standard deviation of my Y variable? And then SX would be standard deviation on X. Okay, so for the slope alone, you need to calculate the correlation between the two variables and the standard deviation for both X and Y. Once we know what the slope is, we can then go ahead and calculate the y-intercept. And to do that, we use this formula here. So when we want to calculate our intercept, we have this formula. What does y bar represent? The mean for y. And x bar would be the mean for x. What is b? That's the slope that I would have just calculated. So when you do the regression line and you're calculating by hand, slope has to be the first thing you calculate because we use it to find the y-intercept. Okay? And this formula here comes from the fact, there's a very important aspect of our regression line. Our regression line must always pass through what's called the mean point. Okay? If I were to draw a regression line through my scatter plot, one thing that I can guarantee if I've calculated the slope and y-intercept correctly is that my line will definitely contain the point x bar, y bar. So it will pass through the exact point where the x mean and the y mean come together. Okay? So since we know that is a specific point that always happens on a regression model, we use that point to calculate our missing y-intercept. Okay? This is a very important aspect right here. You need to know this. Your regression model will always pass through that mean point. Okay? When you graph these, if you're going to have to graph some scatter plots, graph regression lines by hand, this is going to be extremely important because when you draw it, you need to make sure your line passes through this point. I will check that. Does your line pass through where x bar, y bar would be plotted? If it doesn't, it's going to be wrong. Okay, so you need to make sure that when you draw these by hand, you are making sure that you're passing through the mean point. Okay? So know the formulas and know the idea of passing through that mean point. You okay with this? So these two formulas you need to make sure you know. Okay? You will be expected to calculate a regression model by hand as well as on the calculator, and we'll get to the calculator in a little bit here. So, back to our Burger King example. If we want to actually put this into practice here. Now, the first thing you would need to do, if you are going to calculate a regression line, the first thing you have to do is find these 5 pieces of information. So if you were doing this from start to finish, let's talk through the steps. What would be the first thing you'd have to do if you needed to calculate these 5 pieces of information? What would be the steps in my calculator? All right. To get x bar, y bar, sx, and sy, I would put my data into my lists. Explanatory in list 1, response in list 2. Okay? So I'd put those in to my list first. Then I would use the 2-var stats. So in the 2-var stats, I'm going to get x bar and sx on the first screen. If I scroll down, I'll get y bar and sy. So 2-var stats is going to get me 4 out of the 5 pieces that I need. How am I going to get correlation? So this comes from 2-var stats. This comes from what? Linreg. And it's either going to be the ax plus b or the a plus bx, whichever one you decide to choose, right? So one of the things to note here, if you're doing this by hand, if I say calculate the regression line by hand, your very first step after entering the data into your calculator is to do 2-var stats to get these 4 pieces. And then you're going to be typing into linreg, which is going to give you your correlation, right? But the other thing that's going to happen when you type in linreg is it's going to give you your regression line. Okay? If we look at the actual title of the program, it's linreg, linear regression. So you're going to have access to what your equation should look like before you've even calculated it. So something you might do on a process like this, when you calculate correlation, is jot down what slope did the calculator give me, what y-intercept did the calculator give me, so that when you go through the process of calculating by hand, you can match up. Did I come up with the exact same values? If not, I messed up somewhere. If I did, I know I did it right. Okay? So your first step is to calculate these 5 pieces of information. All right? So now, once I have those 5 pieces, my next step is going to be calculate my slope and then calculate my y-intercept. So if I want to calculate slope, I use that formula, correlation times standard deviation of y divided by standard deviation of x. You need to make sure that on these types of problems, one of the things that sometimes gets messed up, pay close attention to the sign of your correlation. If it's a negative correlation, you need to make sure you put that negative into your calculation, because if you have a negative correlation, what does that mean about your association? It's negative. And if you have a negative association, what type of slope should your line have? Negative. Okay? So be aware that when you find correlation, you need to type it in exactly as you have it, positive or negative. Okay? So, correlation, standard deviation of y, 16.4, standard deviation of x, 14.0. We get a slope of 0.97. Okay? Once we have our slope, we can go ahead and plug it into the second part of our equation to find our value for our y-intercept. So for the y-intercept, we take y bar minus slope times x bar. So y bar is 23.5 minus slope 0.97 times x bar 17.2. When we do that, I get a value of 6.82 for our y-intercept. So what would be the last thing I need to do here? Plug it back in and get the actual equation, right? So how is this equation going to look? What would I write? Y hat equals 6.82 plus 0.97x. Okay? So once I know my slope and y-intercept, I can plug those back in. Now notice, when Grace was saying she said y bar is equal to 6.82 plus 0.97x, is it okay to switch order here? Yeah, it doesn't matter what order you go in as long as you have the correct coefficient with the correct part. So slope with x, y-intercept as a constant on its own. So y hat equals 0.97x plus 6.82. Okay? Now, another way to write this, instead of y hat and x, something that might be more useful, give more explanation to the problem, and it's something that I would maybe recommend for you guys as you write these out, is instead of using y and x, we can plug in the actual variable name. And a lot of times that makes things a little more clear as to how I describe certain aspects of the regression model. So instead of y hat, I could call this fat hat. Okay? What that means is this is my predicted amount of fat. So when I am given an amount of protein and I plug it into my equation, I'm going to be given a predicted amount of fat in that particular item. Okay? So instead of x and y, you can replace those with the actual variable names. So x was the amount of protein, y was the amount of fat in an object. So the predicted amount of fat is equal to 0.97 times the amount of protein plus 6.82. On a quiz or test, I'll accept both. On homework, I'll accept both. It doesn't matter which form you use, but like I said, this sometimes helps people visualize and see exactly what you're working with. Because like I said, we want to be able to interpret slope, we want to be able to interpret y-intercept. Okay? So this can sometimes help out with that. Are we okay with the calculation part? And most of it just comes from knowing the formula, plugging in, and then putting it all together. So we okay with that? Blank stares to me means yes. Okay. So, when we use our data here, so now that we have our actual regression line, we go back to that original question that we wanted to answer. Without the regression line, it's an impossible question to answer. Now we have a way to predict how much fat would be in an object given a certain amount of protein. So if I want to know how much fat I can expect to consume with 25 grams of protein, what do I need to do? All right, plug the 25 in for protein. Okay, and this is where using the words will make things easier to see which way you want to plug in. If we're talking 25 grams of protein, we plug it in for protein. That way you don't have to keep track of x versus y. Okay? So, when we look at the calculation here, we plug 25 in for protein. And our predicted value for y, or the predicted amount of fat in that particular item or items, would be 31.07 grams. So if I went to Burger King with the goal of eating 25 grams of protein, I could also expect to eat about 31.07 grams of fat. Okay with that?
So if you solve a problem like the other way and you like plug in a value for y, when you answer it then, isn't your answer going to be a prediction?
If you were trying to do it in reverse order with using fat as your input,
Yeah.
you would have to go back and recalculate all of your pieces based on x and y being flipped. So where your x bar sx and y bar sy were, you'd have to flip those values.
So we're always going to plug in for the one for sure.
Yes, the one that we know for sure. So if I wanted to go backwards and go fat, I would have had to recalculate. I'd get a completely different slope and different y-intercept because now I'd be using fat as my x and I'd be using protein as my y. So yeah, you'd have to recalculate the entire line to go the other way. We can't go from a predicted value Like we don't have a predicted value to go to an exact value. It doesn't work that way. We have to know from a known, that has to be our explanatory for the predicted response. We okay with that? All right, so next part, being able to interpret slope and y-intercept. So getting them is just a matter of knowing the equations, being able to plug in, finding a value. Okay. When we look at the slope of a regression line, the slope is always going to be expressed in terms of units of y per units of x. Now, for what you need to know here, you need to understand how to actually interpret it. When they tell you what the slope of a regression model is, you need to know how to relate it to the context of the question. So this is again where using the variable names in the equation itself helps you to keep track of what you're working with. So our slope of 0.97 in our Burger King example meant that each time I add 1 gram of protein to an item, I'm going to also add 0.97 grams of fat to that item. So when you interpret slope, what you're basically trying to do is say, for every 1 unit increase in x, we see this change in y. So if you want a general statement for that, for every 1 unit increase in x, we see this change in y. So in our particular case, every 1 added gram of protein meant an added 0.97 grams of fat to a specific item. Now, what if I would have, or we would have gone through the whole process here, and we had a slope that was like negative 1.6? So if we had a completely different set of data, our slope comes out to be negative 1.6, then I would say for every 1 unit increase in x, what's going to happen to y? If I have a slope of negative 1.6, if I add 1 extra unit to x, what's going to happen to y? We're going to be decreasing by 1.6 in y, right? So for every 1 unit increase in x, we're going to see a 1.6 unit decrease in y. Okay, so every time you're interpreting slope, that's what you're asking. If I increase x by 1 unit, what's going to happen to y? Does that make sense? Okay. Now, when we change units, so if we had changed our original information from grams to ounces, okay, while that won't affect correlation at all, so if we were to calculate correlation ahead of time like we need to for the by hand calculation, correlation's not going to change because correlation doesn't care about units. But the slope of your equation will, which means the y-intercept of your equation will. So changing units, adding or subtracting values, multiplying or dividing values to a data set, all are going to affect your regression model. They won't change correlation at all, but they will affect your equation. So any change you make to the data is going to affect what you do with your regression line. Okay? And then the last thing here, the intercept. So being able to interpret the intercept. The intercept of a regression line is simply the value the line will take on when our x variable happens to be 0. Okay. Now, one thing to note here, the y-intercept is, for prediction purposes, basically useless to us. There's not a lot of times where x equals 0 is an actual value we're interested in. Sometimes it might be the case, but a lot of times it's not going to be. Also, it sometimes won't make sense what the y-intercept would say when x is equal to 0. So when you're looking at the y-intercept, basically if you have to describe it, you're basically saying when x is 0, this is our value for y. This would be the predicted value. But as far as prediction purposes go, it's not going to be useless, or it's going to be pretty useless to us. It's really just a starting point for our graph. So it's a starting point for the line to go through as it's created. So if we think back to our Burger King example, we had a y-intercept of 6.82. What does that 6.82 actually mean? That's the amount of grams of fat in an item if that item had 0 grams of protein. So if I chose an item that had 0 grams of protein, I could expect it to have about 6.82 grams of fat. Okay, so if you're talking y-intercept, you're always relating it to, if x was 0, y would be this. Okay? So, here we have that same kind of example from before. We want to see if there's a strong association between number of days a student misses and the student's semester grade. So here's our information. Now, we're not going to go through the regression formula again. I think you guys, as long as you have the formula in front of you, you're okay to kind of go through that, right? If I was doing this with the formula, the first thing I would do is type this into my calculator and do what? The 2 bar stats, list x bar, y bar, sx, sy. Next thing I would do is go to linreg and get my correlation constant. So when I have my correlation, then I can plug into my formulas, get slope, get y-intercept, put it together to make an equation, right? So you guys are okay with that process? All right, let's do this instead with our calculators, just so you get some practice with that. And to be honest, doing this in the calculator is the same exact process as calculating correlation. Everything about it. So I want you to put in the values to your list. So number of days absent would be our explanatory. That goes in for x. Semester grade would be our response variable. That goes in for y. And again, you have to make sure you have those in the correct order. Explanatory and response. Before we could flip them back and forth with correlation, we cannot do that with regression. Get those numbers in real quick. And once you do, go ahead and go through the process of finding correlation. So go ahead and choose your linreg ax plus b, or if you want to keep things consistent with your book, use that linreg a plus bx. So if you scroll down to option 8, there's a second option there that you can use as well. Okay, so when you do that, you should be looking at the screen. It's going to give you everything you need. You have your slope, your y-intercept, you have r squared, you have r. Okay, so all that's laying in front of you. So if I wanted to write out the equation for this set of data, my predicted value of y would be equal to, what's the y-intercept for this particular set? 90.8. So the y-intercept would be 90.8 plus, or I guess I should say plus or minus, is my slope. The slope is negative, so minus, what's the slope? 1.98 x. So this is what my equation should look like. Y hat is equal to 90.8 minus 1.98x. Or if we want to use variable names, instead of y hat, I could write this as, yeah, we could do grade hat. So the predicted grade would be equal to 90.8 minus 1.98 times days absent. Okay, so again, both forms work just fine. I typically like this form where we put the variable names in. Just helps keep track of things a little bit easier. So the predicted grade will be equal to 90.8 minus 1.98 times the number of days absent. So let's talk about a couple things here. My slope is negative 1.98. What does that mean in this context? So the negative aspect, it means the more days we miss, the lower our grade's going to be. But specifically, what does the negative 1.98 mean?
How many days
Okay, this slope of negative 1.98 literally means for each additional day you miss, every time you miss another day, your grade decreases by 1.98%. So when you interpret slope, you have to associate it with an increased unit in x and how it affects y. So every additional day you miss a school, your grade goes down 1.98%. Okay? The y-intercept is 90.8. What does that mean? If you don't miss any days, you would get a 90.8. Now, in this particular case, would that necessarily make any sense for us? Not really, because we noticed that one person missed 2 and scored a 93, right? So it wouldn't necessarily make sense completely for the start of our grade to begin at 90.8. Okay? So again, it's more of just a starting off point for our equation. It doesn't necessarily give us anything useful as far as prediction purposes. Okay? So now, if this is our equation, predict the grade a student would get if they miss 14 days of school. So our predicted value, if we put in 90.8 minus 1.98 times 14 days absent, what could that student expect to get based on this relationship? What? Okay, so about 63.1. So they could expect to get about 63% in the class if they miss 14 days. Okay? So, here's our regression model. That's how we use it to predict. So we plug in values for x, find predicted values for y. Now, the next thing I want to talk about, this is the last thing here. We have this idea of what we call extrapolation. Now, the main goal of creating a regression model is to use that equation to predict values. However, those predictions are only accurate within the scope of the data we're looking at. Extrapolation is something that occurs when we start trying to predict things beyond our given data. So we have a certain range of x values that we can work with. We measured values from this low x value to this high x value. If I start plugging in values below or above what I actually looked at, can I guarantee that the trend I'm currently looking at continues on in either direction? No. So when we try to extrapolate, when you see people trying to predict outside of the scope of what things are happening, a lot of times they can be inaccurate. We can't trust those predictions because we don't know what happens to the pattern outside of a given interval. So the example I always use is age versus height. As you get older, what tends to happen as far as height goes? It goes up, right? So think about from the time you're a child to about now, usually. You generally get taller every year, right? Some of you grow faster or slower than others, but in general, every year you get taller. Now, if I tried to use that same model, so let's say I came up with a model to predict a person's height at age 13. Okay? So that would be something we'd be able to predict fairly accurately, probably. But what if I tried to predict their age using that same model at 50? Yeah, that model says they're going to continue growing. But what do we know always happens? At some point, you stop growing. And in fact, after you hit a certain point, you actually start shrinking, right? So once you hit about, is it usually about 25 or something like that, 25 to 30? You actually start shrinking from then on, okay? So with that type of problem, guys, always keep in mind, if you leave your scope, your predictions may not be accurate because the trend might change. With height, it follows a linear pattern for a while, but at some point it's going to level off and then actually start to kind of go down a bit. Okay? So we can't extrapolate without having some issues. So your assignment is going to be a worksheet. Yeah, I didn't have a chance to staple these, so on your way out, just grab a worksheet. It's 2 pages. If you want to staple real quick, I have a stapler over there, but I didn't have a chance to get them stapled beforehand.
I had a question. I think this was the day I missed for these two.